first implementation that we are going to discuss is this edge list implementation. So how it works is we can represent the graph in the form of edges. So in this case, we have this edge, which is from A to B, that's value is 10. The next one is A to C, the value is 15, and so on. So this is a weighted and directed graph. So we can represent this graph in the form of a data structure which stores all the edges, one per row. In this case, we could have like a 2D array where we can store these things, where the first index might store uh, like the array is of size n cross 3, where n is the number of rows or the number of edges in our case, and 3 is the 3 columns that we have, which is the from, to, and the weight, if the graph has a weight. Now let's discuss the common operations. Like we can represent this entire graph first, which is our graph G, which has 1, 2, 3, 4, 5, 6, 7, total 7 edges in the form of a 2D array, which looks something like this. Each row represents an edge. Now, this is the entire representation of graph, but let's discuss what would be the cost of common operations if we were to implement this. Like you can implement this in multiple ways, not only an array, like not only a 2D array, you can also implement this in the form of a set, which we are going to discuss in the future. Also, you can use a vector to solve this, but typically the time complexity of these common operations will remain the same, because conceptually the way it is being represented, it should have some minimum cost to it. Which is, let's discuss the first one, which is what if I want to check whether A is connected to B? So how long will this take? So just pause your video and think about how long will it take to check whether A is connected to B, and how long will it take to check what are the A's adjacent nodes. So I hope you have paused the video and like thought about this. So let's discuss one by one, which is if we want to check whether A is connected to B, you need to traverse this entire array to see whether A and B are there in this entire array. So it's going to take at least O of E time to check this in the worst case, because the array's size, which is like if we are implementing it as a 2D array, the number of rows is going to be variable, and the number of rows is actually equal to the edge, the number of edges, because the total size of the array is going to be the number of edges times 3, where 3 is a constant. So we don't care. So if you want to see if two nodes are connected or not, it's going to take O of E amount of time. Now we discussed the fact that when we are discussing the properties, this E is almost proportional to V square, because let's say if the graph is well connected, and if this has V edge, V vertices, then like let's say if A is connected to a lot of other nodes and the graph is dense, then this is proportional to V square, which is like, this is a really basic operation. And if it is taking like O of E or V square time, like it is not that good. The next one is adjacency, which is what are A's adjacent nodes. Again, like since this array might not be sorted, like even if it is sorted, like you need to sort them, it takes like n log n complexity to sort the things. But let's assume that it's not sorted. So again, you have to traverse each of the rows and find out the rows which have A's on the left. In case of a directed graph, like if this was a directed graph, you had to check both, like this left one and the right one, to make sure it could be on either side. So this is again going to take like O of E time to find what are A's adjacent nodes. Now when we are talking about the space, like how much space will this consume? So it's going to consume like E which is the number of edges, times 3, which is again like simplified to O of E. So the total space it will consume is O of E. And in the worst case, all these three operations can be approximately equal to O of V square, like if the graph is pretty dense. So that's why like this is a really costly way to represent our graph. So we are going to discuss the next type of implementation in our next video.